Okay, so let's keep trucking. So finally, we get our Swift punchline. So here's our final picture here of what all of our historical languages kind of look like. And I said that Swift, its job is not to make Objective-C people happy. You know, it's not really the upgrade to Objective-C. I mean, it effectively ended up being that for folks, but I don't think this was the real motivation. Swift looks far, far, far more like C Sharp and Java than it does Objective-C. Swift, if I want to print something in Swift, okay, not this crazy stuff up here. So Swift looks like Java. It looks like C Sharp. Swift looks like JavaScript. It looks like Python. It looks like Node.js. It looks like Ruby. It looks like PHP. So the real thing is, this is Apple saying, hey, Android developers, come over to the dark side. It's Apple saying, hey, Python developers, stop writing HTML5 mobile applications. Why don't you come write native stuff for iPhone? All right, so it's the gateway drug to get all of these developers in the rest of the world who are using these other technologies an easy path into coming over and writing stuff native for Apple technologies. Their flagship Apple technology, which would be iPhone, right? iPhone and iPad. So I mean, certainly, you know, the Mac itself has their own app store, but that's, you know, far, far less popular. I mean, I've put several hundred apps on the Apple App Store for iPhone and iPad. I have 0 apps on the Mac App Store. So, what's my motivation to put stuff on the Mac App Store? Lots of people have iPhones. Very few people have, you know, Macs, relatively speaking. So that's where the market is in their mobile stuff. So that's the punchline for Swift. See, I give a 10-minute break, and he comes back 19 minutes later.
There was a huge line.
You're practicing cricket, weren't you? A huge line for what? Coffee? You didn't bring me any coffee.
I brought a candy.
I can't eat candy. That's carbs. It's a double whammy. It's against them. So I yell at. You guys know Shiva? So I yell at him. He always bring. Well, yeah. The guy came in and stole my other soda. He every single time he sees me, he wants to bring me something. I don't know why, but he does. And he keeps bringing me stuff that I'm not supposed to eat. So I'm on a low carbohydrate diet. And, you know, I'm not supposed to eat carbs. He brings me cake and candy. I mean, I'm also a fat guy, so, you know, I like cake. Right? Who doesn't like cake? So my wife yelled at me yesterday because I ate half a cake at lunch. He brought me a cake. You're gonna bring your professor a bribe present. Bring him something that he can eat. Well, no, bring him something he's supposed to eat. All right. So that's the punchline for Swift. Now let's get into our variables and stuff, because we have some stuff to do in order to get to our enough material for our homework, because our homework for next time is hard. There's 4 parts to the programming assignment. The first 3 are easy. First 3 are basically identical to each other. So once you figure out one, the next 2 are easy. The last one, though, it's like the worst parts of the Bible. I mean, it's always been a rough one. I hate solving it because I can only get it right half the time when we do it in class. It's terrible. What if that was true? How mad would you be? Teachers giving you homework they can't do themselves. All right, so let's talk about variables. So the general concept of a variable, and remember we go all the way back, just as a reminder here, we talked about how human beings solve problems, right? and we said that we use our memory, we ask questions and repetition, and then there's a mapping. So every single programming language, 100% of them, implements or has a way of representing memory, usually through variables, asking questions through conditionals, and then repetition through loops, methods, procedures, subroutines, blah, blah, blah. Now, in your homework assignment for today, you had to use variables and asking questions, right? Okay, so I'm going to kind of gloss through those pretty quick since you kind of saw some of this in the video, but you said you didn't see the size stuff in the video for like size of bytes and shorts and ints and longs. Okay, so I'll cover that pretty quickly and then solve your homework for you real quick. Was the homework easy? Huh? It was like on a scale of 1 to 10, how hard was the homework? 7? 7 being hard? You're going to come back with an answer of about a 40 next week when you see this next homework. 40. See, she got coffee and she's only 23 minutes late.
She's behind me.
How long could the line be at 8 o'clock at night? This is in the library, right?
Like I asked for 1 coffee, she charged me for 2.
Oh, so you had to fight. You had
I
to.
had to wait
So
for.
she got a fight with
No, I didn't.
Did you
fight.
throw a phone?
So it was like peace out.
I shattered my brand new phone. I threw it in her face. All right, so 100% of languages have these mappings. So let's quickly fill this out for. These are going to be variables in Java. All right, so I'm going to show you our variable types in Java. So Java, and let me call these primitive type variables because really, well, let's go this route. Variables come in 2 flavors. So we'll start off by saying variables are name value pairs where the name must start with a character cannot have spaces and has a few other rules that the compiler will scream at you about if you screw up. All right. So when I say name value pairs, it's like, A is equal to 7. So 7's the value, A is the name value pairs. Okay? Variables come in 2 flavors. We have primitive types and we have object types. Now, we already talked about strongly typed languages versus loosely typed languages, right? So strongly typed languages are languages that require us to identify the kind of value variables built to hold before we use the variable. Java is one of those guys. All right, so Java is a language that whenever we create a variable, we have to say, this dude is built for holding this kind of stuff. All right, and our options for that type are going to be any of our primitive types, which I'm about to show you, and then any object type, which is literally an infinite number of things since we can write our own objects. All right, we'll get to object types, we'll get to our first object type later tonight because I have to introduce some stuff to you, but for primitive types, a definition for these guys are can only hold a value. That's it. Okay? They're a built-in variable type, built into the language, and all it can do is hold a value. Object types can potentially hold one or more values and potentially do more. Okay, so you have a lot of flexibility with objects, but with great power comes great responsibility, blah, blah, blah. All right, so forget about object types just for the moment. I want to talk about primitive types first because that's really what we needed to know for our homework assignment, right? Actually, homework assignment, you had to do conditionals, variables, and loops, right? All right. All right, so let's do primitive types. And these are really the Java primitive types, but this is pretty much identical to the C primitive types, right? Because these all came from C. So This list is going to be C, C++, Java, C Sharp, all the same. All right, so we have byte. Don't capitalize stuff for me. How about that? Can I turn that off? Short, int, long, char, float, double, Boolean. The only one that changes in some of these languages is Boolean. So in C, Booleans were actually represented as ints, zeros and ones. In C++, they were bools, B-O-O-L. In Java, it's Boolean. In C Sharp, it's bool with a capital B. Yeah, like that. They're basically all the same thing. Okay, so Boolean is true or false. These guys are used for Boolean expressions, which was in last week's video, right? So Boolean expression is any expression that boils down to a single value of true or false. And we use those in our conditionals, and we use those in our loops. Okay? So let's look at these guys here. So byte, short, int, long, char. Well, let's just start with these. Byte, short, int, long. These guys all hold whole numbers, right? Was that in the video, that part? They all hold whole numbers? Okay, so then I'll gloss over this pretty quickly. So these guys hold 8-bit values. These guys hold 16-bit values. These guys hold 32-bit values. These guys hold 64-bit values. And these are signed integers. Integers. So I really didn't put the size of these on the video. But I covered the rest. I covered that these were whole numbers.
We talked about truncating.
Yeah, well, that's when I do math with these. But it just surprises me that I wouldn't have talked about the size. So I didn't talk about Y2K bug or anything like that? Really? Okay. All right. So 8-bit signed integer, this guy can hold plus or minus 2 to the 7th power. So when I say something is signed, that means that one of those bits is going to be used for the positive or negative. So it can hold positive and negative numbers. So this is negative 128 to positive 127. Actually, yeah, that's correct. 16-bit, this is going to be negative 32,768 to positive 32,767, which is plus or minus 2 to the 15th power. 32-bit, this is negative 2.1 billion to positive 2.1 billion, which is plus or minus 2 to the 31st power. And then long is negative, well, actually it'd be negative tiny number to positive huge number, which is plus or minus 2 to the 63rd power. All right, so it's that number. So 9.22, I think it's quintillion. So negative 9.2 quintillion to positive 9.2 quintillion. Big number. All right. Now, so all of these values, bytes, shorts, ints, longs, are all built for holding whole numbers. Okay, whole numbers. Why do we need so many different ways of holding whole numbers? What do you think? Why might I use a byte versus use an int? Space, okay. How much do we care about space? How much memory do we have in our computers today? 8 gigs, 16 gigs, stuff like that? Well, I got to remember these guys came from a language from 1968. So these primitive types have been around for a while. And they were just inherited from language to language to language. So do we have 8 gigabytes of RAM in 1968? little bit less. In fact, back in the 80s, there was a famous quote by Bill Gates that you'll never need more than 32 kilobytes of RAM. Kilobytes. Okay. So if you have 8 gigabytes of RAM today, we're going to say 8 gigabytes is about your common laptop today, right? 8 gigabytes is, right around the middle of the road for a nicer laptop, I guess, but they go higher. You can get 16 gigs in a laptop. That means that Bill Gates' comment that you'll never need more than 32K of RAM, our common case today is 262,144 times bigger than Bill Gates said we would never need. He was wrong, right? All right. So back in the 60s and 70s and 80s, memory was A, at a premium, B, very, 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 very expensive. Okay? So it was very important for a programmer to pick the correct size type to hold the value they needed to hold so that it had the smallest possible memory footprint that they needed, right? Today, we just say, throw it in an integer. If it doesn't fit, put it in a long. If it doesn't fit in there, let's go and look at the object types and look at like big integer or something, which is an arbitrary size integer in Java, where it gets slower as you hold gigantic numbers, but you can just keep putting stuff in it. But that's today's mentality, because memory is cheap, right? If you have a laptop that came with 4 gigabytes of RAM and you could upgrade it to 8, how much is a 4 gigabyte chip? $25, $30? Not expensive, right? Back in 1996, I had a computer with 8 megabytes of RAM and I wanted to double it. So I got an 8 megabyte RAM stick in 1996. So we're saying 4 gigabytes is about $30 right now. That's 4096 megabytes. So 512 times the size of what I bought in 1996. So $30 gets you 512 of what I bought in 1996. How much do you think I spent for that 8 megabyte chip in 1996? If I could buy 512 of them today for $30. Think $500? I would have loved it was $500. Spent $1,000. $1,000 on an 8 megabyte chip. And that today's dollars, so this is 4096, that's, and that divided by 30, actually, I need to use 30 divided by that, right? 30 divided by 4096 is that per megabyte times 8. So 6 cents. That chip is 6 cents in today's dollars. I spent $1,000 on it in 1996. And you know what is shocking? Memory had already started coming down in price. It would have been more expensive the year before. Actually, it might not have been available the year before. But relatively speaking, you go back to the late 60s and the 70s, fractions of what our memory is today would have cost thousands of dollars. Okay? If you could even buy 8 megabytes of memory in the 70s, it would cost us like as much as a house. If it was available, if you could even buy that much. Expensive. Really, really, really expensive. So when we put things in those terms, we can understand that earlier programmers had to be pretty diligent about this. Okay? Now the reality is today, nobody uses a short. It's basically dead. The only time you'll see a short is when you've copied code off Google. So you might want to give your stolen code a little once over before you submit it if you have some shorts in there. All right, nobody uses shorts. Bytes are still used, but for a different reason. Nobody uses bytes because they like, oh, I only have to hold the value between negative 128 and positive 127. They use bytes for like video streaming stuff because things are coming in one byte at a time. So it just happens to be kind of a compatible size bucket for what's already coming in. Otherwise, your common go-to move for a programmer today is if you need to hold a whole number that's signed, it's an int. And if it won't fit in there, you use a long. Now, let me come back to char in a second. Floats are similar. Floats and doubles are similar in that a float is, let's see, it's 32-bit before the decimal point, 16-bit after the decimal point. And a double is 64-bit before the decimal point, 32-bit after the decimal point. Okay, so float is like an int. Double is like a long for decimal numbers, like 3.14 or that kind of stuff. Also signed, so it can hold positive and negative numbers. So that 32 bits is actually plus or minus 2 to the 31st, same as int. The 64 bits double, that's plus or minus 2 to the 63rd. So that's going to be just like a long. But what's after the decimal place would be unsigned. You don't have negative, you don't have signs after the decimal place. So 16 bits, you get the full 16 bits, 2 to the 16th power. And the 32 bits, you get the full 32 bits, 2 to the 32nd power. All right, so yeah, so this is 0 to 65,535 is what 16 bits is, and this is like 4.2 billion, something like that. Okay, but what's interesting is I've mentioned that in today's world, the go-to move is typically an int. In the floating point side of things, the go-to move is typically a double. It's interesting. It's interesting that it happens to be the case. So you will rarely see floats used in modern programs, especially Java. I would say it's extremely rare in Java. But with that in mind, since we're not always using numbers up into the billions, we're probably wasteful fairly often in terms of memory. We don't care. We've got 16 gigs of it. Bring it. Right? So this is part of the reason why I talk about some of this historical stuff, because it's important that we understand that this isn't the way it's always been. Okay, that we do need to be good stewards of our memory and things like that. Because even though the common problem today doesn't make us think about this, there are still problems today that do. Okay, 16 gigabytes of RAM is not an unlimited amount of RAM. You can run out of that much RAM in your computers. In fact, this is the new MacBook Pro, and people complained that the maximum amount of RAM you could put in this thing was 16 gigabytes. It's a brand new machine. It's supposed to be forward facing. You should be able to put at least 32 gigs of RAM in it. Why can't you? My previous MacBook Pro was from 2012. It also had 16 gigabytes of RAM in it. Made sense in 2012 that your maximum maybe was 16 gigs. That was impressive in 2012. 2017, nobody's like, drooling over my 16 gigs of RAM. In most rooms, I'm at least tied for the most amount of RAM in a laptop. Anybody else in here have 16 gigabytes of RAM in their laptop? Nobody? You do? Anybody have more? 32? It does exist in laptops. Not that often, but it does exist. But punchline is that this is the brand new, latest, greatest thing that Apple charges $4,000 for. You should have bragging rights, right? I shouldn't have the same amount of RAM I had in 2012. Screen's pretty nice, plus I have the almost non-functional thing, except for we found the arrow guys today, right? Nailed it. It was awesome. So exciting. I got to tell all my friends. All right. So that's the float and double thing. Just common use is people typically, if they need to hold a floating point number, they put it in a double. This convention. Now char. This guy is a 16-bit unsigned integer. So when we think about characters, we're thinking about them like as A and B and C and question mark, things like that, single chars. But we actually represent them as 16-bit unsigned numbers. So that means this is a value of 0 to 65,535, okay, which is 0 to 2 to the 16th minus 1. That's what that value is. So there's 65,536 unique characters. Anybody know why we represent the character, the char primitive type as a unsigned integer rather than stored as characters? We have this thing called character maps. And in older languages like C and C++, chars were actually represented as 8-bit unsigned values. So 0 to 255, 256 unique characters. Okay, this is actually character sets. So anybody know the name of the character set that has 256 unique characters? Any of you have like a t-shirt that has it on there? ASCII. All right, so American Standard Code for Information Interchange. Okay, then all of a sudden we woke up one day and decided, you know what? There are more languages in this world than English, right? Most of us in here know that, right? Now, having said that, the rest of the world was a little bit, slow to catch on to that because the rest of the world decided just to learn English to deal with the dumb Americans, right? The way it went. We were too stubborn to learn anything else, so it's just, whatever. But we did get a new character set, and this is something called Unicode. All right, so Unicode is an expanded character set. So the first 256 characters in Unicode are the ASCII character set. All right, so Unicode is a superset of ASCII. Then you have a whole bunch of characters from all sorts of different languages, symbols and things like that. I don't think every single language that exists on Earth is represented, but a lot of them are. And actually, what's even more depressing for the whole dumb American comment is the ASCII didn't even use all 256. I mean, we had smiley faces in there and like playing cards. We just started throwing stuff in there. It's just fun, right? You would have thought that maybe, given our proximity to a couple of countries, maybe we throw Spanish in there, or, the French alphabet, because you got some French places in Canada. No, just let's throw smiley faces in there. Oh, sometimes history is funny. It's just, and sad. So in any case, this char primitive type is meant to represent, in this case, Java represents the Unicode character set, and so does Swift. Most of our modern languages are going to represent Unicode. Actually, Swift goes even farther. Swift allows you to have variable names with emojis in them. Why? I don't get it. Well, actually, maybe now I will get it, because now I have like the super emoji thing. Was that this class that I found the tennis ball? Oh, it's so good. Watch this. Type tennis, and then I get So now I can just, I'm coding on iPhone, and I can, if I want to name a variable, I can, but I want to have it be the tennis emoji. I can just type in tennis, and then I get the picture shows up here. It's the tennis ball. I'm going to just leave that up there because it makes me happy. What was I doing? Oh, character sets, that's right. So, computers like numbers, right? So, instead of trying to teach a computer how to remember an A or remember a B, that kind of stuff, we instead say, hey, here's a big index of numbers. This number happens to map to an A. This number happens to map to a B. So I'll tell you what, we're going to give you the number that we want. And because this is a strongly typed language, and because we advertise that this variable is a char, before you spit it back to us, why don't you go ahead and do a quick lookup and spit out the character associated with that number rather than the number itself. All right, and let me actually show you an example of that right now since we're getting ready to segue into. So did we use Eclipse for our homework? Okay. So I think I introduced that in the video, right? Eclipse, got you the download and all that stuff. All right. Do I have it? Yep. Nailed it. Is this the newest one? Neon? You just installed it. Or you're still kind of enamored from the tennis ball. Me too. All right. So let's go ahead and create a new Java project. Spring 2017? That this year? All right. So here's our folder. I'm going to go ahead and give myself a new file in here. And usually when I create that first class, I usually call it driver. This allows us to, I usually do it to connect some of the dots when you think about software drivers that make your, your USB mouse and stuff like that work. I mean, it's a program that is the starting point for doing something. So since this is the guy that's going to have our main method in it, I like calling it driver, but you don't have to, just whatever. So I'll call this guy driver. You could also cheat here and click this little button that puts the main method in there, but I would encourage you not to do that for a while. All right, make sure you get used to being able to create that blank template. So, when something first opens here, you can do it. All right, awesome. You want to be able to jump into this guy. All right, so you should be able to write your quick little hello world program, just make sure everything is working, and being able to start with a nice little quick template like this in many languages is kind of a good skill set to have, because then once you have this, you can add stuff to it pretty easily. And you hit the little play button and you get your hello world down here, and we know everything is peachy. All right, makes sense? In the video, did I talk about this guy here? That's for command line arguments?
Yeah, a little bit.
Like, did I show you an example probably?
No.
Okay. Doo-doo. I hate this keyboard right now. So under traditional settings, if you're going to compile a Java program, this is effectively what's happening when you hit that little play button in Eclipse. It's compiling your file, and as long as nothing bounces back with any sort of errors, you're getting, let me just do you get a new file here called dot with a dot class at the end of it. To run that guy, you do Java test, and there's my hello world. So now those command line arguments. Let's go back into this guy. By the way, this is a text editor called VI. This is how people used to program instead of using, and then this is how cool kids program. We're using VI. VI is because you actually have a command line with this. Like to save stuff, you hit escape, then colon, then WQ, right quit. You feel powerful, like you're really using your operating system, right? All right. I started on something like this when I was like 9 or 10, so it's very natural for me, except I don't like my escape button as like not a button anymore. It's this magic thing. So I don't like that. That's because I always have to hit escape before I put in my command. So now I'm starting to hate this, but whatever. But this allows me to show you the command line arguments. So these guys, traditionally, these are called args, for arguments. All right. And Shiva said he's going to sacrifice a big goat later for stealing my soda. So you're going to confirm this, I guess? I actually have a picture of him holding a goat skull at the store he works at. He's a weird dude. So these guys are for command line arguments, because you got to remember that historically these programs were not launched by like double clicking on something. They were run from the command line, and you might give it some inputs. All right, so for instance, we'll just write a quick little for loop. Ay, ay, ay. I do hate this keyboard. I've decided. Huh? I gotta get a new laptop. That's true. This is Apple's new, whatever they call it, the Butterfly 2 keyboard or something. I have a feeling the buttons must be millimeters different distances apart than my previous one. So I keep missing, because I don't type normally. If you watch me type on this side, I'm like hitting keys with weird stuff. I type fast, but my hands are too big for like normal touch typing. I'm like a monster. Plus, I learned how to type when I was very young, so it's basically like a praying mantis typing. I think I hit the space bar with like 3 or 4 different fingers. All right, so what this for loop's going to do is it's going to just go through whatever is inside of this this collection. So an array, this is a string array. It's a collection of stuff. So depending on how many command line arguments I give this guy, that collection will be anywhere between 0 and whatever. All right, and all I'm going to do is I'm going to print out each thing, so you'll see that how command line arguments can work. So I'll go ahead and save this. And since I made a change, I need to recompile it. Okay, then I'm going to run this guy. And if I don't give it anything and I just run it, it does nothing. But if I do cat, dog, and I run it, it prints out cat and dog. 2 arguments. I gave it the argument cat. I gave it the argument dog. Cat came in bucket 0. Dog came in bucket 1. It printed out cat and dog. That's what those command line arguments are for. Okay, and those guys are actually, something I'll say fairly often is all programs begin and end with main. Okay, so we have this thing in here, this main method. All right, and the main method is also a throwback to C. So if we go back, and if I, let's just do test.c. Do I still remember how to write a C program? Yay. All right, that should be, then at the end I got to do just run this real quick and make sure it. So there's hello world in C. So if I go back into this guy, notice that main here actually takes 2 separate parameters. An integer and this guy right here, a char pointer, that is a string array. A char pointer is a string, so that leads to the beginning of a bunch of characters, and then char pointer is a collection of strings. Now, what we're seeing here is historically in a language like C, a much older language, arrays did not know their own length. If you go back to my code over here, we only had a single guy here because that array is able to advertise to us how many elements are in it. So in here, the two parameters that get passed to main are the argument count, the number of arguments, as well as that guy. So let's see here, I'll mimic it here. Actually, depends what flag I have on. Let me just set that to, just so I don't have to do anything else special. I think that will work. All right, so this is a loop. It's going to go take I between 0 up to argc, the number of arguments, and each time through it's going to print out the string contained in bucket I of this argument array. I think that should work. I might need to use some pointer syntax depending on the version of GCC on this. So, oh, actually, this is an interesting historical thing. Notice it printed out 3 things because the first command line argument is actually the name of the program. So this was bucket 0, this was bucket 1, this was bucket 2, where Java doesn't give you the name of the program. So you're just seeing some historical things, how these guys connect. Make some sense? Kinda? Okay, so tell me what's confusing. Actually, maybe let me connect some dots for you. Let's do this. Let's say, so if I type ls, there's a bunch of things there. Actually, maybe Dropbox will make more sense. So I got a bunch of stuff in my Dropbox folder here. Now, think about each program I write as being one of these little commands. Like you were doing the things like with dir or ls. So when I do ls, this gives me a directory listing. Somebody at some point wrote a C program named ls. All right, so when you type in ls with no other arguments, that's what it does. But now, if I wanted to have ls do something more, so I can say lsw star. Now it only shows me the stuff with w's in it. Okay, and it even goes into some of the folders. I can also link programs together. So for instance, in that one, I gave it a command line argument. I gave it the w star command line argument. I can say, so again, there's ls. I can say ls, I want to take the output of that program. I want to pump that into another program called grep. And within that program, I want to look for anything that is, let's just do w star there. Okay, so it's showing us that we have some, the 3 things, these are directories, so it can't go into those. But, you know, punchline is that this is the result of that program. So this is a program, and rather than having the output go to my screen, I'm having the output, this is the pipe character, I'm piping into this program, and this program takes in a command line argument. Similarly, somebody at some point wrote a program called VI, the text editor I've been using. VI won't work if I just hit VI. Okay, I need to tell it the name of the file I want to edit. So if I were looking at the code for VI, you'd have in there an if statement. So if command line arguments is equal to, or if the arg count is equal to 1, that means you only gave it the name of the file, then give an error saying, hey, you know, usage, I think if I just say VI, it probably is going to give me, you know, how you use this thing. Otherwise, when you do VI, you type in the name of the file, what it's going to do is it's going to say, okay, you gave me the name of the file, let me go and look in the directory, find a file with that name, bring it into the buffer, do all the VI magic stuff and give you a text editor to work in. But it couldn't have found your file unless you had told it that command line argument. So that whole mechanism for accepting those arguments is something that's left over from a long time ago. It's kind of off our radar today because we typically don't run programs like this, right? We just double click and everything just magically happens. Although many of those programs still can take command line arguments, because what ends up happening is that shortcut that we have when we double click it, it's giving full command line arguments. For those of you who play some of these video games, you can go in and do some of the different settings and stuff like that, and then you hit the button that says play, and that's what actually launches the game client. I guarantee all those settings are turned into various command line flags that are being sent to the client, so the client starts up in the correct mode, with the right graphic settings and all that stuff. All right, so under the hood, all this stuff is still happening. We just don't really see it, so it's off our radar. All right, but we just saw this is something that's stuck there from 1968. That still exists today, but realistically, you're probably not using command line arguments in Java very often. But they exist, and I like naming that guy Elephant. Okay, the whole rest of this whole public static void main thing needs to look just like this. Well, you can put whatever you want in here, but this variable name can be whatever you want. But when you use it, you just need to make sure you reference it by the name you gave it up there. So homework assignment was to loop between all the numbers between 1 and a million. Okay, and then ask some questions along the way. So let's start with that. So I need a loop. I is 1. I is less than or equal to, that's 100,000. That's a million. I plus plus. And we decided that we needed to count how many numbers fulfilled a certain requirement. Okay, so I need to, every single time we go through, I'm going to say, oh, that's 1, that's 2, that's 3, whatever. I need to store that somewhere. So I'm going to need a variable to hold that. So I'll create an int count, start that guy off at 0 because I haven't found any yet. And then I'm going to ask my question. So I want to know if I, the current value of I, because I is going to be 1, then I is going to be 2, then I is going to be 3. That's what this loop does. It takes I on that voyage between all the numbers between 1 and, in this case, 1 million, because this guy's going to keep going until I is not less than or equal to 1 million. Okay, that means as soon as it hits 1,000,001 is when this will finally fail. All right. And what were the numbers?
9, 13, 27, and 81.
Okay, 9, 13, 27, 81. Okay, so if I mod, if I mod, you said 9 is equal to 0, and it's an or, right? Or I mod 13 is equal to 0, or I mod 27 is equal to 0, or I mod 81 is equal to 0. If any of those are true, even if multiples are true, if any of those are true, then I want to increment my count. So count is equal to count plus 1. After this for loop is finally over, then we can print out our final count. All right, and what number should it be? That one? Yeah, I program so slow on this keyboard. It's just garbage. I mess up constantly. Need more tennis balls. I don't get it in this program. Well, that sucks. All right. So, questions about this. So this little assignment gave us practice using conditionals. Right here, we asked a question, and kind of a complex question, right? We're saying if this value, when we divide it by 9, has a remainder of 0, that means it's evenly divisible, or, so if this is true, or this is true, or this is true, or this is true, if any of those are true, then go ahead and increment count. All right? Now, one interesting thing to point out here is, let's say I had the value 9, for example. Let's say I was 9. 9 mod 9. 9 goes into 9 one time with a remainder of 0. So this part right here would be true, correct? It will not waste time checking the rest. Okay? It will not waste time checking the rest, because with ORs, only the first, if any individual part, if at least one part is true, the whole thing is true. So it would be poor performance to keep checking if we're already allowed in. That makes sense? And that's actually an important thing. And let me do this just so you have a copy of this solution in case you want to use mine. I'll put it in Slack. What was this? Homework 2 solution? Something like that? Whatever. Okay. So some interesting things that I guess you can do with that, though, is let me introduce strings. We're going to start talking about strings today, and I want to make sure we get far enough into them. So any questions in this code before I delete some stuff? So everybody could reproduce this given some time. Okay. Now, one of the things, like I said a few minutes ago, is make sure you're always writing main out right now to get practice. Don't copy and paste too much of your code. Next time you have to write a for loop, write it from scratch. Okay. Once you find that boring, okay. Once you find that, I'm just going to go and grab it from over here and bring it in and modify it because I already know what I'm doing, then you can do the copy and paste thing. Okay. But until you've got the muscle memory down, okay, or you get a new keyboard, type it as often as you can. Okay, because that's the best way. The way many of you learned English is by speaking it, right? Okay, so that's the way you do it. Keep typing this stuff, and you'll find that it gets a lot less frustrating. Because right now you're fighting two different wars. Okay, you're fighting the "Hey, I'm a beginning programmer" war, and "Hey, I'm just learning Java right now" war. So in any given situation, you might know what you're doing, but not know how to write it, or you might know how to write it, but not know what you're doing. Like, I can write a for loop, I just don't know what the for loop should be. That's usually the thing with beginning programmers. You start getting the syntax down, but you just don't know how to solve problems. You're like, oh, okay, well, I could write you a for loop. I don't know what I'm supposed to put in there, but I can write it. Okay, so I promise you'll get better over time. I also promise, like I said before, you are going to hate me this week. Because the fourth part of the programming assignment is just insane. It's way too hard. But I do get enjoyment out of seeing the suffering. So, I would encourage you to work in groups and ask questions, but most of you aren't going to do that. And then you're going to come back crying next week, which I will also find enjoyable. Okay, you want me to lie? That's one of my hobbies is during final exam week when you sit there and you're just waiting for a student to crack. You get somebody crying in the audience. I had one person last year just sob for like 45 straight minutes. Then hand in a blank test and walk out. I had so much trouble just not sitting here like cackling. And I think the class average was like an 88 or something. The exam wasn't bad. She just wasn't prepared. That was a highlight of that day. All right, so who is this guy? All right, so let's introduce strings. So we have this this thing called a string, and this one's there's my tennis ball. Okay, we have this thing called a string, and strings are actually a little rough, given that they're the first object we introduce. So we're going to say first object we look at, but doesn't really act like most objects. And that's what makes it difficult. Java is a string-based language. It's something I'll say very often. So if we can get something into the format of a string, strings are very malleable. We can turn it into other things pretty easily. All right. Well, with that in mind, Java recognized that and they said, you know what, we're gonna treat strings. We're gonna treat them differently. Okay. Most objects are gonna act identically to each other, except strings. They're gonna act a lot like primitive types. But they're objects. But they won't act like objects. Okay? It's actually kind of it's an important caveat, and it actually makes it difficult because strings are they almost have to be the first object we look at because they're really important. But because of the way Java treats them, I kind of lull you into this idea that this is how objects act. And it's only this one that acts that way. So let me kind of show that by an example. And what I'm going to end up doing here is I'm going to show you something that works, but I'm not going to tell you about it yet because I want to introduce the new keyword later. But just so you see the difference. All right. So I'm going to say string S. There we go. Let's put it. We'll say string A is equal to hello. Then we're going to say string B is equal to new string hello. And then we're going to say random R is equal to new random. Like that. And this is going to want me to import java.util. All right. Now I'm going to print these three things out. A, B, and I guess R. I don't know why I didn't say C, but whatever. What? Okay. So A looks like the string hello. B looks like the string hello, although I created it a little bit differently. I created this second one in a way that looks kind of similar to this last one guy and this last guy, right? This new keyword, this is the guy I'm not going to tell you about yet. That's probably a next class thing. All right. So there are two different ways we can create strings in Java. The traditional object notation way, that guy that looks just like any other object, or I usually call this syntactic sugar. Java gives us a nice shortcut where we can create strings just like we create integers. Int a equals 7. Okay? Because strings are important, so we're going to give you a nice friendly syntax for it. Problem is it can run us into trouble. Okay, I'm going to show you some examples here in a few minutes. First of all, anybody want to predict what the output of this will be? Those 3 lines? Like it'd be a random number? Yeah. Okay. Tell me more about this random number so I know whether you're right or wrong.
We did give any seeds to it, so it would be any random number.
Okay, so some number in the range of integers, so negative 2 billion to positive 2 billion. Okay, good, you're wrong. But good, you fell for my trap. So this is going to be hello, as he pointed out. This is going to be hello, as he pointed out. This is going to be a memory address. Okay, so when I run this, there's our hello, hello, and here's crazy memory address. Okay, it is kind of a random memory address, but it's not a random number. The random number you're looking for would be this guy. Using one of the abilities of that random object to give us a random number. Okay, so there's our random number. But what we would have expected, if I'm saying, so just giving away a little bit here, if when I created this guy using the new keyword, I got a memory address, because the foreshadowing is this. The new keyword is our real estate agent. It goes and finds memory for us. Okay? So if I use the real estate agent to find this memory, and I use the new keyword to find this memory, why did this guy have hello instead of a memory address? And why did this guy have a memory address? All right? So that's the evidence that Java treats strings differently. Okay, so that's fine. Just accept that as strings are a special case. They act more like primitives when you pass. And also, having said that, we talked about pass by reference and pass by value. Okay, strings are passed by value. All other objects are passed by reference. So that means if we change a string inside of a method or a function of some type, it does not have side effect. It will not change back in its original location. Every other object would. All right, so objects in Java are passed by reference. Their memory address is sent, with one exception, and that's strings. Strings are passed by value like all the primitive types. Okay, so they're just a special case. Just kind of remember that. You're going to use strings pretty often, so you'll get that drilled into your head, but try to compartmentalize strings as primitive types that can do things more like objects instead of objects that act like primitive types. But they are an object. Now, having said that, let me show you a common beginning programming mistake. Comment out that line for right now. We'll leave it out. Let's just hit you with both of them right off the bat. All right, so what kind of animal is that? What would the result of what I have highlighted there be? A Boolean value. So that's a Boolean expression, right? Any expression that boils down to a single value of true or false. All right, and that's that double equal sign. That's the Boolean equivalence operator, correct? So we have A is equal to hello. We have B is equal to hello, correct? So what Boolean value will this boil down to? You think false? Okay. You think true? All right. What Boolean value will this guy boil down to?
False.
False? You think two falses? What do you think? Two trues? Nobody's right yet.
So one is false and one is true.
Good guess. Okay, which one?
First one is false. Second one. First one is false
First one
and
is
second one
true,
is true.
second is false.
Yeah, she's right. She doesn't know why she's right, but she's right. Yeah. All right, so let's see it first and then I'll explain. So there's your true and there's your false. Okay? First of all, this double equal sign is the primitive Boolean equivalence operator. It's for comparing primitive types. Strings are object types. So when I compare a string to another string using this operator, I'm not saying, does this string, is the contents of this string the same as the contents of this string? I'm asking the question, is the memory address of this object the same as the memory address of this object? Do they point to the same place in memory? Now, what's interesting here then is why the first one was true and the second one was false. All right, I'm going to give you a chance to redeem yourself. All right, so we're going to go ahead and we're going to say string C is equal to hello. And then we'll go ahead and we'll just copy this guy and we'll give ourselves a new third one. So forget about these first two. What's the result of this last one going to be?
False.
Think false?
Yeah. Because those memories are not pointing to the same.
I gave him a chance to redeem himself. What do you think? Did you get it right? You willing to bet your grade on it? Real high roller. You said false, right? It's true. It is true all day long. Okay. Now, this is where the value of understanding how things are happening under the hood comes in. All right. The issue is he's had some programming before, so he knows enough to be dangerous. Is the issue? So when he originally said this first one was false, he answered false for the right reason, but he had the wrong answer. So this guy right here, is called a string literal. All right, just like the number, so if, for instance, if I say int I is equal to 7, this is an integer literal. That's a solid hard-coded value, right? 7 is 7 is 7 is 7 all day long, right? So built into our computer, we have the value 7 stored somewhere. Okay, we don't, if you have 10 variables all holding the value 7, do we store 7 10 times, or we just have them all reference that same literal 7? They all reference the same literal 7. Why spend extra space for something that doesn't change, right? The number 7 is not going anywhere. It's going to be 7 tomorrow. It's going to be 7 next week. Okay? So this type of value is called a literal, a constant, if you will. This is the string literal hello. The first time we create that in this line right here, when I say string A equals hello, what's happening behind the scenes is Java is going and looking and saying, it has a board back there and saying, oh, here's my board of string literals. Do I already have hello up here? I don't. So I'm going to go ahead and add it at this memory address right here. Okay? And I'm going to let A know that that's where he lives. Okay? Now, when we get to this guy right here for string B, since I use the new keyword, that's our real estate object. Our real estate agent finds new memory. At that point, we're not going to look at our literal board because we've explicitly said, look, I want new memory. Okay? Even though it's the same blueprint, I want a different house than that guy's house. Okay, so we specifically asked for new memory. So we're not going to check our literal board here. We're going to go out and grab some new memory over here somewhere and put our string hello there. Okay? This last guy here, string C, again, it's a string literal. We didn't use the new keyword. Okay, so an important lesson here is that even though these both mostly produce the same result, they're not identical. They're not completely interchangeable. Okay, I'll talk more about that as we look at some examples. Go ahead.
So without saying it has to be a new address, does changing one string change?
It does not. Good, excellent question. It does not because they are, it does not because they are passed by value, and that's probably the reason why they're passed by value, is to protect the constant table, or the literal table we have here. So this last one, we create string C, we're setting C equal to the string literal hello. Well, we go to our board. Is hello already up there? It is. So I'm going to take that memory address, I'm going to give it to C. So after that line, A and C, they don't hold strings that say the same thing. They hold the same string. Okay? They both hold them, they're objects, so they hold memory addresses. And they both hold the same memory address, which points to that one place on that literal board. Okay? Which is why when I say A equivalent to the literal hello, well, we're going to go to our literal board. We're going to say, oh, well, here's where hello lives. Then we're going to say, what does A hold? A holds that same memory address. Those are the same. It's not looking at the HELLO. It's looking at the memory address. Does that make sense? That's also why this guy is true. A points to that place in the on the board. C points to that place on the board. Same pointer. We didn't look at HELLO. Right? Look at the memory address. But B equal to hello. This guy right here lives up on the board. That's his memory address. But B lived over here because we used the new keyword to build them. Make sense? That lesson that you just learned is probably known by less than 20% of professional Java developers. Because professional Java developers would not use that double equal sign. Pretty rare to use that double equal sign in Java when you're dealing with objects because it's wrong. The only time you would write it this way is if you actually wanted to compare the memory addresses. Not do these guys contain the same stuff. You're asking the question, are these guys the same? Are they literally the same? Make sense? So if we wanted to compare, for instance, B being equal to hello. We would say B dot equals hello. So strings have built into them a method called equals that allows them to compare themselves to other strings. And this guy returns a Boolean value of true if the two strings have the same content, and false otherwise. There's also an equals ignore case if you want it to be case insensitive. Okay, so now this line here will return a true because B, which lives over there but contains the string HELLO, is equal to the string HELLO, which happens to live over here. They contain the same stuff. So that's what we really meant to say. But when we use that double equal sign improperly, we actually were saying something else. So there's 3 truths. Make sense? Okay, so we just introduced a string method. We introduced equals. I'm actually going to write it with its return type. So this is Boolean equals another string. So any string can call his own equals method, which allows you to pass another string to it, and it will compare those guys for their content. All right, so we're kind of limping into being able to read the documentation here. At some point, some point very soon, I'm going to take you into the documentation. It might happen tonight, but at the very least, I want to make sure I introduce all the tools you're going to need for the homework. Okay, let's take a 10-minute break. I'm starting, 12 minutes. I'm starting at 9. So be back by 9 or they're going to miss the stuff. All right.